In 1999, NASA lost a $125 million Mars rover because when it got to Mars, it basically blew up. The reason it blew up was because half of the people working on the rover and the rocket to get it there were using metric units. They were using meters and newtons and things like that. And the other half of people working on it were cavemen. They were using imperial units, or as the NASA website puts it, English units. So thank you for that. What happened was the calculations went wrong, because when one person is sending something in miles and the other person is expecting kilometers, it doesn't work very well. And this is why I wanted to start my discussion on mechanics and physics as well, talking in depth about units, because units are very, very important. And I'm not saying that being an annoying teacher telling you to make sure you write them at the end of a problem. I'm telling you because in real life, if we don't all agree on what units to use, our numbers have no meaning, right? So I'm going to go at this from a mechanics and physics standpoint, and we're going to go over the 7 SI units, which are the, and pardon my French, Signifie International units. Got back from France last week, don't know if you could tell. And these 7 units are the ones that we will always be using in our mechanics and physics problems, unless for some reason it is otherwise stated. So I'm going to go through each one, explain some of the maths behind each one, when we're going to use it, how to convert them, and then also a little bit of history, because some of these are a bit weird. So let's start off with mass. Whenever we measure the mass of something, we use kilograms. The kilogram, 1,000 grams, that is our significant unit, our SI units for mass. No matter what it is. If you are an astronomy student working with planets, then the Earth has a mass of 6 times 10 to the 24, I think, yeah. If you are, working with electrons, then it has a mass of 9 times 10 to the minus 31 kilograms. We always try and work in kilograms unless otherwise stated. So, they should be nice and easy, okay? But I wanted to use this as an opportunity to mention the difference between mass and weight. Mass is the amount of stuff an object has inside of it. The amount of kilograms an object has will not change. It will stay the same no matter where it is, no matter what it's doing. It will always have that mass. Weight is how that mass is affected by gravity, by a gravitational pull. When an object is on Earth, it is being pulled down with a weight. That weight is mg. It is a force. It is the force that is pulling you towards the ground, that is pulling everything towards the ground, that is pulling the Earth around the sun, etc., etc., etc. And it is the product of its mass in kilograms times by the gravitational field strength. I'll probably make a video detailing gravitational field strength when I start talking about gravity in the physics videos, but this is more of a bridge between maths, mechanics, and physics. G will take one of 3 values. If you are a high-level physicist, it will be 9.805. If you are just, an A-level student or an early years physicist, it will take a value of 9.8. And if you are a GCSE student or an engineer, it will take a value of 10. That is the strength of the gravity of Earth. On the moon, it's 1.6. On the sun, it's probably a lot more than that. I don't know off the top of my head. Now, where do we actually get the kilogram from? Because the whole point of these SI units is that we can use them no matter who we are, where we are on the planet. We all know what a kilogram is. And until very, very recently, I think it was 2019, maybe a bit earlier than that, the kilogram was defined as this big block of metal that lived in Paris. And that block of metal had a mass of 1 kilogram. And that was it. If you wanted to know what a kilogram was, you've got to go to Paris and have a look at this block of metal. Now they've defined it a bit fancier, but that was where we got the idea of a kilogram from. Now the next one is length. How do we measure the length of something or the distance between it? Well, it is measured in meters. Measuring the distance between here and the sun, we measure it in meters. Measuring the distance between two protons, we measure in meters. And if there's any of you that are going to hit me with an Armstrong or a nanometer or something, that's fine. But in general, we like to use meters. So, meters aren't too difficult to grasp. I'm not going to spend too much time on that. I'm sure you know how they work. Millimeters, centimeters, decameters, kilometers, etc. We can all convert them into meters. Nothing too fancy with this invention. I believe the meter was invented 17th century France. They defined it as 10 millionth of the way between the equator and the North Pole. And I'm not entirely confident they knew the exact distance between the equator and the North Pole. But we've now kind of honed that in and we've got a nice definition of a meter. The next one is Kelvin. If you are just a math student, skip ahead a couple of seconds because Kelvin is a very physicsy term. It is a unit of temperature. It is the unit that we all use in physics when referring to something's temperature. We don't use Celsius, that's what we use in our day-to-day lives, and we don't use Fahrenheit, that's what we use when we're living as cavemen. They are two very different things that we don't use in a physics setting. We use Kelvin. Kelvin is the same scale as Celsius, so a difference of 1 Celsius is the same as a difference of 1 Kelvin, but it starts at absolute zero. The lowest possible value of Kelvin that you can have is 0 Kelvin, which is equivalent to minus 273 degrees Celsius. 0 Kelvin is the coldest anything in the universe can be. If you get to 0 Kelvin, something's gone wrong, everything's stopped. And that is where we get Kelvin from. Okay, welcome back math students, because now let's have a look at the next one, which is time. Time is always measured in seconds. I don't care what we're doing. If it's the orbital period of the Earth, it is measured in seconds. If it is the amount of time it takes for some uranium isotope to decay, we are measuring it in seconds. If it is the distance traveled by a car at a certain speed, it is measured in seconds. A couple of conversions that it's always useful to remember. Seconds to an hour is 3,600. To get that to a year, 3,600 seconds in an hour, 24 hours in a day, 365 hours in a year. Days in a year. Yeah, if you want to be more specific, you can have 0.25 for the leap years, but this will get you the amount of seconds in a year, and we can use that to find age of the universe or, I don't know, what else? Age of the universe, time taken for stars to move. I don't know, I'm not an astrophysicist. The way we define a second, by the way, it's weird. Basically, we took a cesium-133 atom and we looked at it and we noticed that as every atom does, inside it there are little vibrations between the shells of electrons, okay? And we decided that every 9,192,631,770 vibrations, that's a second. That's one. Yes, sir. That's 1 second. That's the definition of a second. That many vibrations in a cesium-133 atom. I don't know how they come up with it either. Weird. And before you ask, no, I did not read that off a whiteboard that I have positioned under the camera because I can't remember that number. That would be ridiculous. So, these are the 4 kind of main ones. If you're a chemist, you may be familiar with a mole. I am not a chemist. I use these exclusively in thermodynamics and that's about it. Can't stand chemistry, no offense if you can. Moles are the amount of stuff in a substance. The amount of a substance. See, my pen's jumping all over the place because I hate it as well. 1 mole of something has exactly 6 times 10 to the 24, a bit more specific than that, atoms of a substance. In physics and mechanics, I'm probably not going to be too worried about this, but it's still very useful to know, especially in thermodynamics. 6th one is the ampere. Again, if you're a maths mechanics student, this is not going to be useful to you at all. If you're a physicist, amperes are what we measure electrical currents in. Everything else we do in electricity can be formed out of all of these, but an amp I will go into more detail in a physicsy video later. I'm not going to waste too much time here. And then finally, we have this, the candela. It's a thing. The candela measures the brightness of something. That's fun. Yeah, the reason I'm being incredibly sarcastic is because I have a degree in physics. I've taught physics for many years. I did an A-level in physics, and I have never once in my life seen the word candela written down in anything remotely important. I know I'm going to get corrected, and there's many, many important things that a candela is written in, but if you're doing A-level or if you're just doing normal physics, this probably isn't going to be that important. But, you know, that's just my opinion. So, these are our 7 SI units, all defined in different ways, but the whole point of them is that no matter where I go on the planet, no matter who I'm communicating with, I always can work with the same type of numbers. I'm not getting my miles and my kilometers mixed up. It all works out very nicely.